Zero-point energy, ZPE, is the lowest possible energy that a quantum mechanical system may have. Unlike in classical mechanics, quantum systems constantly fluctuate in their lowest energy state, as described by the Heisenberg uncertainty principle. Therefore, even at absolute zero, atoms and molecules retain some vibrational motion. Apart from atoms and molecules, the empty space of the vacuum also has these properties. According to quantum field theory, the universe can be thought of not as isolated particles, but continuous fluctuating fields, matter fields, whose quanta are fermions, leptons and quarks, and force fields, whose quanta are bosons, photons, and gluons. All these fields have zero-point energy. These fluctuating zero-point fields lead to a kind of reintroduction of an ether in physics, since some systems can detect the existence of this energy. However, this ether cannot be thought of as a physical medium if it is to be Lorentz invariant, such that there is no contradiction with Einstein's theory of special relativity. The notion of a zero-point energy is also important for cosmology, and physics currently lacks a full theoretical model for understanding zero-point energy in this context in particular. The discrepancy between theorized and observed vacuum energy in the universe is a source of major contention. Yet according to Einstein's theory of general relativity, any such energy would gravitate, and the experimental evidence from the expansion of the universe, dark energy and the Casimir effect shows any such energy to be exceptionally weak. One proposal that attempts to address this issue is to say that the fermion field has a negative zero-point energy, while the boson field has positive zero-point energy, and thus these energies somehow cancel out each other. This idea would be true if supersymmetry were an exact symmetry of nature. However, the Large Hadron Collider at CERN has so far found no evidence to support it. Moreover, it is known that if supersymmetry is valid at all, it is at most a broken symmetry, only true at very high energies, and no one has been able to show a theory where zero-point cancellations occur in the low-energy universe we observe today. This discrepancy is known as the cosmological constant problem, and it is one of the greatest unsolved mysteries in physics. Many physicists believe that the vacuum holds the key to a full understanding of nature. In classical mechanics, all particles can be thought of as having some energy made up of their potential energy and kinetic energy. Temperature, for example, arises from the intensity of random particle motion caused by kinetic energy, known as Brownian motion. As temperature is reduced to absolute zero, it might be thought that all motion ceases and particles come completely to rest. In fact, however, kinetic energy is retained by particles even at the lowest possible temperature. The random motion corresponding to this zero-point energy never vanishes. It is a consequence of the uncertainty principle of quantum mechanics. The uncertainty principle states that no object can ever have precise values of position and velocity simultaneously. The total energy of a quantum mechanical object, potential and kinetic, is described by its Hamiltonian, which also describes the system as a harmonic oscillator or wave function that fluctuates between various energy states. See wave-particle duality. All quantum mechanical systems undergo fluctuations even in their ground state, a consequence of their wave-like nature. The uncertainty principle requires every quantum mechanical system to have a fluctuating zero-point energy greater than the minimum of its classical potential well. This results in motion even at absolute zero. For example, liquid helium does not freeze under atmospheric pressure regardless of temperature due to its zero-point energy. Given the equivalence of mass and energy expressed by Albert Einstein's E equals mc square, any point in space that contains energy can be thought of as having mass to create particles. Modern physics has developed quantum field theory, QFT, to understand the fundamental interactions between matter and forces. It treats every single point of space as a quantum harmonic oscillator. According to QFT, the universe is made up of matter fields, whose quanta are fermions, leptons, and quarks, and force fields, whose quanta are bosons, photons, and gluons. All these fields have zero-point energy. Recent experiments support the idea that particles themselves can be thought of as excited states of the underlying quantum vacuum, and that all properties of matter are merely vacuum fluctuations arising from interactions of the zero-point field. The idea that empty space can have an intrinsic energy associated with it, and that there is no such thing as a true vacuum, is seemingly unintuitive. It is often argued that the entire universe is completely bathed in the zero-point radiation, and as such, it can add only some constant amount to calculations. Physical measurements will therefore reveal only deviations from this value. For many practical calculations, zero-point energy is dismissed by fiat in the mathematical model as a term that has no physical effect. Such treatment causes problems, however, as in Einstein's theory of general relativity. The absolute energy value of space is not an arbitrary constant and gives rise to the cosmological constant. For decades, most physicists assumed that there was some undiscovered fundamental principle that will remove the infinite zero-point energy and make it completely vanish. If the vacuum has no intrinsic, absolute value of energy, it will not gravitate. It was believed that as the universe expands from the aftermath of the Big Bang, the energy contained in any unit of empty space will decrease as the total energy spreads out to fill the volume of the universe. Galaxies and all matter in the universe should begin to decelerate. This possibility was ruled out in 1998 by the discovery that the expansion of the universe is not slowing down, but is in fact accelerating, meaning empty space does indeed have some intrinsic energy. The discovery of dark energy is best explained by zero-point energy, though it still remains a mystery as to why the value appears to be so small compared to the huge value obtained through theory, the cosmological constant problem. Many physical effects attributed to zero-point energy have been experimentally verified, such as spontaneous emission, Casimir force, Lamb shift, magnetic moment of the electron, and Delbruck scattering. These effects are usually called radiative corrections. This was all for today. Thank you so much for keeping up with us. Join us next time in the next video. See you soon.